proofs of theorems 1.1, 1.2, and so on. I'm very briefly going to just quickly remind you of where we were when we stopped, and that links through to what we're going to do now. Now, if you weren't there at yesterday's lecture, or you wish to review the contents of it, remember I am recording all of these, so do go to the Moodle page. The Moodle page, you can click this badge here, which takes you through to the Google Plus page. On the Google Plus page, there are recordings of all the lectures I've been doing. And posted in comments underneath the lectures are links to any of the paper sheets I produced during the lecture. Okay? So replaying the lecture, although the resolution on the video when it's pointing at the screen and me doing the pen and paper isn't that great, but with the completed sheets there, you can be looking at those and listening to the lecture. You can get quite a good replaying of the lecture. Okay? So do use that to review this material and to help you get to grips with some of the things we were doing. Now, what we did last time was we took this formal definition of convergence, which we introduced the time before last. This is definition 1.6 on page 6. And this is the formal detailed definition of convergence. It introduces this parameter of epsilon. Epsilon is a measure of how close you are to the limit. And it introduces this idea that no matter if a sequence is converging to a limit, so xn converging to the limit L there, written in the definition, what that means is given any positive value of epsilon, think of epsilon as a small number, given any degree of closeness to the limit, if you wait around long enough, once you wait for the arrival of this integer capital N, eventually you'll find that at every point past that capital N, the sequence is at least that close to the limit. Okay? That inequality there, absolute value of xn minus L, that's the distance between the sequence element xn and the limit L. It's saying that that distance is going to be less than epsilon after some point n. Okay, so the definition says, given any epsilon, you can find the n. If that is true, if given any epsilon, you can find the n, then the sequence does indeed converge to that limit. Okay. Now this can be used. This is used in at least two ways. The first way is in proving the convergence of particular sequences. And in the lecture where I introduced this definition, we proved, using this definition, that 1 over n converged to 0 as n goes to infinity. We proved it by demonstrating directly that that sequence 1 over n and the limit L 0, that satisfies that definition. In fact, that might be the only particular sequence that we jump in and demonstrate that it satisfies the definition for, because we can then use properties of convergence. And that's the second thing that the formal definition is used for. It's used for establishing, for justifying, properties about convergence itself. So not talking about individual specific sequences, perhaps like this one, but just the phenomenon of convergence itself. So this is what we were doing yesterday morning. Okay? We proved that theorem 1.1, that limits were unique. If a sequence is convergent, there can only be one limit for it. We did that by a proof by contradiction. Okay, the proof is it's in yesterday's lecture, and my notes are there that I produced during the lecture. This is the proof of it. We did a proof by contradiction, so we suppose that a convergent sequence had two distinct limits, L and M. We showed that from that, contradiction arises. And the principle of proof by contradiction then says that that assumption must be false. So limits are unique. We then proved that theorem 1.2, that every convergent sequence is bounded. Given any convergent sequence, there will be a limit somewhere. There will be a definite finite interval on the number line so that the whole sequence is contained within that limit. Okay? They're bounded. And then the most interesting one, we started proving theorem 1.4. Theorem 1.4 allows us to say something about the convergence of complex sequences, knowing something about the convergence of their parts. We proved the linearity case. We'll do some examples of this afterwards. The linearity case says, well, if you have two sequences, a sequence AN converging to the limit A, here in theorem 1.4, a sequence Bn converging to the limit B, But if you make a new third sequence, so this is a new third sequence described here, given some value of alpha and beta. Alpha and beta are fixed coefficients. You take alpha times the first element, an, plus beta times the second element, an. That combination is going to be the element of your new sequence. Well, the theorem says that new sequence you construct, it will be convergent also. It's convergent because the parts that it was constructed from are convergent. And the limit that it has is the limit you'd expect. Alpha times the limit of the first sequence plus beta times the limit of the second sequence. Okay? If you form a third sequence by combining the A and the B sequence in a certain way, the limit that comes out is the corresponding combination of the limits. Okay? So that principle is called, that's an example of the general phenomenon of linearity. You'll see linearity crop up all over the place. Whenever you do something to a sum, and that's equivalent to doing the thing to the individual parts of the sum and then adding the results together, that's, in general, is termed linearity. Okay, so we shall proceed now onto the second part of this theorem, which is the product form of 1.4. So what are the assumptions? The assumptions are that we have two convergent sequences, an and bn. An is converging to A, bn is converging to B as n goes to infinity. I'll try and record this. So that's the assumptions. Good. So this is the setup. This is the information we're starting with. An converges to A and Bn converges to B as n goes to infinity. We want to prove that if you make a new sequence now, you make the new sequence by multiplying together corresponding terms of the original two sequences. So I have a new sequence, an multiplied by bn. Okay, so for instance, this would be the sequence. The first element would be a1, b1, second element a2, b2, third element a3, b3, etc. This is the sequence of elements a and b. Okay, the two parts multiplied together. Okay. Now, what do we expect? What kind of behavior do we expect from such a sequence? Well, we're assuming that the first factor in the product is getting closer and closer to some limiting value represented by A on its own without a subscript. And the second factor, the Bn, is getting closer and closer to some limiting value B. So if you had to guess what the limit was going to be, there's really only one possible guess you could make. If it's going to be at all connected to the behavior of an and bn, surely it has to be this. The limit of the first part multiplied by the limit of the second. And you can kind of convince yourself of it by saying, well, the A1, the A2, and the A3, they're getting closer and closer to A. B1, the B2, and the B3, they're getting closer and closer to B. So surely the product will be getting closer and closer to A times B. And that intuition is not wrong, okay? But I don't think it constitutes a proof. I don't think it constitutes a rigorous argument that this has to be true, because we've already seen, when we examine particular sequences, we've already seen that some sequences can converge quite fast. Other sequences can converge relatively slowly, at a much slower rate than other sequences. So it could be this AN is converging extremely fast to A, but the BNs are taking a very long time to get anywhere near to their limit. So how do these different rates of convergence behave when you multiply the things together? Okay? Funny things can happen when you multiply parts together. Maybe it won't end up getting closer and closer. We want a rigorous argument. Okay? And we can get a rigorous argument by making use of the formal definition of convergence, because it has a parameter in it that definition, the epsilon parameter. You can use that to represent degree of closeness to the limit and argue accordingly. Okay? So that's what we're going to do. But as is often the case, we're going to break down a complex problem, make it simpler, break it down into parts first. Okay? So I'm going to take the view that this is maybe too hard to prove in one single step. So I'm going to prove just a specialized version of it, first of all, and then I'll use that specialized version to prove the general version. Okay? First, we'll consider the special case. When the two limits are both 0. Okay, so that's a particular type of situation. We're dealing with two sequences that are convergent to 0. Now we want to show that AN BN converges to 0. Okay. And what do we know? Let's write down the formal definition of convergence as it applies to these two sequences. Okay? We know that given any epsilon greater than 0, so any positive epsilon whatsoever, there exist integers n1 and n2. n1 is going to do the job for the A sequence, n2 is going to do the job for the B sequence, such that for all n greater than n1, the absolute value of an is less than epsilon. Okay, normally we write absolute value of the sequence element minus the limit. The limit is 0. So I won't bother writing in minus 0. Just talking about the absolute value of the an. Eventually, it gets this small. And no matter how small someone asks for it to be, no matter how small a number epsilon somebody gives you, there will be a point beyond which the sequence elements get that small. ST means such that. Sorry, it's such that. A acronym. And the similar thing for the B sequence, such that for all values of the index bigger than n2, the absolute value of Bn can get that small. That's what we know, because we know that two sequences are convergent to 0. Okay. We have to prove the similar thing for the product. So let a value of epsilon greater than 0 be given. Leave a bit of a gap here. Leave a bit of a gap there, so I want to fit something in before these two lines. I want to make this an, the absolute value of an times bn, I want to make that, maybe you might want to pause about taking this down. I want to make it strictly less than epsilon. I'm going to put the strictly less than on a separate sheet, so I might have to move it around depending on how I fill it in. Okay? This is what I have to do. If somebody gives me this value of epsilon, I have to find some point such that for all values of the index little n bigger than or equal to capital N, this absolute value is going to be strictly less than n. That's right. How am I going to do it? Well, I'm somehow going to have to use behavior of the two sequences on their own in order to do this. First of all, what's a good way you can rewrite the absolute value of an times bn? What might be a sensible way to break that down or to express that in a slightly different way, which will allow us to proceed? Anybody got a suggestion for that? So in place here, I'm considering what the absolute value of an multiplied by bn is. Given what's written on the page, is there a sensible way you can re-express that? Be brave, shout it out. Break them apart. So you've got the absolute value of AN times the absolute value of BN. Indeed. The absolute value of a product of two numbers is equal to the product of the absolute values. Now, why is that sensible? That's sensible because now it's a product of these two things, and I'm able to control their sizes because they're converging to 0. So I can make these two things as small as possible. And I want to make them as small as possible so that when you multiply them together, you don't get anything bigger than epsilon. So how small should I make them? We need someone else to be brave. If I want the product to be less than epsilon, how small do I have to make each one of the two? I'm able to make them as small as I want because they're converging to 0. So how small should I make this one? And how small should I make the second one? If I want to make the product of them less than 100, how do I ensure that the product of them is less than 100? If I can control the size of both of them. How small do I make the first one and how small do I make the second? Be brave, shout it out.
Square root of epsilon.
Square root of
Epsilon.
square root of epsilon. So if you want to make the product less than 100, well, and you're able to control each part, well, you make both of them less than 10. If you make both of them less than 10, you know, when you multiply them together, they will be less than 100. Here, we're trying to make the product less than epsilon. But I'm able to control both parts, so indeed, if I ensure that both of them are less than the square root of epsilon, then when you multiply them together, they will be less than epsilon. See, I'm able to do that. So I know that there exists an n1 and n2, such that for all n greater than or equal to n1, the absolute value of an is strictly less than the square root of epsilon. So n greater than n1 implies this inequality, and n greater than or equal to n2 implies the absolute value of bn is less than the square root of epsilon. Now I've got two capital N's. I've got an N1 and an N2. So how do I manufacture the one capital N that I need here for my conclusion? We saw it in the previous proof. How do I choose this capital N? I want to make sure that they're both less than the square root of epsilon. The maximum of the two. Yeah. So if I choose capital N to be the maximum, whichever one of n1 and n2 is the biggest, if I choose n to be the bigger of the two, then if the index little n is bigger than capital N, both of these, yeah, and I've got the less than in the right place, both of them are less than the square root of epsilon. Square root of epsilon times square root of epsilon is, of course, equal to epsilon. So what I want to take from that is this thing is strictly less than epsilon. That's what the formal definition of convergence says I have to prove, and there it is, I proved it. Using the fact that both sequences, sequence AN converges to 0 and the sequence BN. For another language, we're trying to prove that AN times BN gets to 0. We're trying to show that we can make it as small as we want. Right? That if you wait around long enough, it will get as small as you want, as small as you desire. If you want to wait around a bit for it to get less than epsilon, you just wait around long enough to see the first factor get less than the square root of epsilon. And also, if it hasn't happened yet, wait around a little bit longer until the second factor gets less than epsilon. Then you're multiplying together two things which are less than epsilon, so the overall product is, less than the square root of epsilon, so So the overall product will be less than x. Okay. So this is the formal definition. So by the definition of convergence, it's good to put down the conclusion. We know that an times bn converges to 0. Okay? Now that's a special case of the product form of the algebra of limits theorem because it only applies to sequences that are converging to 0. But sequences don't have to converge to 0, they could be converging to anything. So what happens when they're converging to something non-zero? Okay. So now we'll tackle the general case. So we let an converge to A, bn converge to B, with no restriction now on the limits A and B. There can be any number. What about these two sequences? What about an minus A and bn minus B? What do they converge to? Quick answer. What does an minus A get closer and closer to? No. An is getting closer and closer to A. So an minus A is getting closer and closer to 0. Bn as well. So this shows you now I'm going to make use of the special case I just proved. So we can say that the limit as n goes to infinity of the product of these two is equal to 0, using the special case I just proved. See, we're not doing an epsilon argument, because we don't have to. So using the special case we just proved, these two, you can call them shifted sequences. So I have a general sequence an, general convergence sequence, general convergence bn. I shift them both by a constant amount, a and b, respectively. Now I've got two sequences that are converging to 0, so I can say the limit of their product is equal to 0. But now this is begging to be multiplied out. Okay? So this is equivalent to saying, well, I'm going to multiply all of this out, get an an bn, that's what I'm interested in, get a minus a bn, get a minus b an, and I get plus a times b. Just multiply out the brackets. And this looks good because this term here is what I'm interested in. I want to know what the limit of that is. And I want to show that it's equal to a times b. But I've got a limit of all of this stuff. Now, do I know anything that can help me in this situation? Is there any tool we have at our disposal? Saw it not too long ago. You were down in Jeffrey Mountain at 9 o'clock yesterday, if you saw it. We know that the limit operator is linear. Okay, we proved that yesterday. Quickly recap this one. Here I've got a limit of a linear combination, a bunch of stuff added together. Okay? So I can say the limit of all of this is equal to the same combination of the individual limits. So the limit as n tends to infinity of an times bn. That's what I'm interested in. I can have minus a times the limit as n goes to infinity of bn, minus b times the limit as n goes to infinity of an. Remember, see, a on its own and b on its own, they're just fixed constants. They're like the alpha and beta in the linearity result. If you look at the notes, first part, the linearity part, I have those coefficients alpha and beta. Well, here A and B are playing that role, or minus A and minus B. They can come outside the limit operator. And finally, I've got this constant term here. Well, what's the limit of a constant? The limit of a constant is just that value. So this is plus AB here. I've got a 0 still on the right-hand side. This is great progress, because here I have the thing I'm interested in, the limit of AN times BN. Previously, it was buried inside here. Yeah, I could see that that's what I was interested in, but there was all this other junk added onto it. Now I have it on its own, this limit. This is what I'm trying to prove is equal to A times B. But I know what this is. I know what the limit of Bn is, B. And I know what the limit of AN is, it's A. So when you look at what you have there, it's minus AB minus BA plus AB. That's all equal to 0. So what do you get when you simplify that equation? You get the limit of the product is equal to, it's on the right-hand side, AB, A times B, which is exactly what we want, as required. That's the statement we're trying to prove. That's what's on page, near the top of page 7, at the very top of page 7. Limit of AN times BN is equal to A times B. That's quite good. That's more or less 2 pages for that proof. Good to see a 2-page proof. This is your third week in university. You've also seen a 2-page proof by now. Take note of the way we proved it. I set out clearly at the top of the first page there. I set out clearly what we had to do. Given AN converges to A and BN converges to B, prove that AN times BN converges to A times B. Okay. Move it on to that. Oh, sorry. I see. Okay. So the limit of AN times BN is equal to A times B. So we looked at the general case of what we have to prove, which is this statement down here. Well, we decided to make it a bit easier, to approach a simpler case first. And that simplest case was when both sequences were converging to 0. And we had this idea, which came from the audience, of looking at the square root of epsilon. Correct idea. So then we proved the result in that special case, the sequences that converge to 0. Then we were able to prove the general case. We didn't have to be working down at the technical level of an epsilon argument, because we proved enough already to just operate with those new tools. The tools we used were using the special case above. So we took our general pair of sequences, formed the shifted versions of them, which converge to 0. So immediately the special case applies. The limit of the product of these two is equal to 0. Then, sorry, I didn't write it in, but the thing that took us from here to here, this step, this was using the linearity part. Linearity part of theorem 1.4. Okay, what we proved yesterday. So when you take the limit of any linear combination, any bunch of sequences added together, or sequences multiplied by fixed constants, you can break up that limit of that sequence as the limit of the individual parts. The fixed constants can come outside the limit sign. Then those two are, that's B there, that's A there. When you look at the equation then, it all simplifies out. You've got limit of AN times BN is equal to A times. Okay, good. Any questions or any comments on that, or clarification you'd like, or anything unclear about how we put it together? I mean, it is quite a lot to take in. The analogy with literature or something is it's like a big poem. You can read it. You can say, yeah, I know what they're talking about, but there's lots more to be gotten from studying it further. Okay, because there's the issue of how all the little bits fit together, how each bit follows on the next bit. So do study it further, and just like you might learn a poem off by heart, you know, test yourself with, can you sit down the following day and reconstruct the proof of it? Now, it's not a case of learning it off by heart. It's not what I want people to do, although that can be a part of it. But rather, you're trying to understand the proof, remember the general principles being used, and then you can reconstruct it from those general principles and thinking through it rigorously and mathematically. Any clarification I could give? Questions? Okay, good. So, that still leaves the quotient form to be proved. I'm not going to do that now, so I want to leave that for you to do as an exercise. So I'll show you now a sheet that we're going to use. Where is it? It's in the comment to yesterday's lecture. I kind of thought I might give it out yesterday, but I didn't get to. Okay, so I'm going to send you home with this shortly when we finish this afternoon. So as it said, this is a guided construction of the proof of the quotient form of the algebra of limits theorem. So I got these sheets to hand out to people, so I'll leave them down here when you're going. So this sets out the objective of trying to prove the quotient form. To prove that the limit of a quotient is the quotient of the limits. The limit of an over bn is equal to a over b when an is converging to a and bn is converging to b. Now, immediately when you start looking at quotients, you immediately have to add in some extra conditions, safeguarding the fact that, well, you don't ever want to think about a fraction with 0 underneath, okay? Because doesn't mean anything. Can't divide by 0. So this only applies in the case where the second sequence bn is not converging to 0, so the limit b is non-zero, and we have this extra condition that none of the terms of the sequence bn are 0. So it stays completely away from 0. In that case, the quotient rule applies. The sequence an can be close to 0 or converge to 0 or sometimes be equal to 0. An's be equal to 0. That's okay, but just the ones in the denominator count. And this sheet guides you through a number of steps, kind of takes you by the hand and leads you through the discovery or the construction of the proof of this. Okay? And again, it breaks down the problem. So let's just look at that first step. So first it says, show that the theorem can be derived using the product form, which we just proved completely, product form of the algebra of limits theorem, and this special case of the quotient form. Okay, so the same idea. We're looking at a special case first. So the special case is just to prove it for the 1 over version. So if bn converges to b, what the rest of the steps are is getting towards the proof that 1 over bn converges to 1 over b. Now, assuming we can do that, assume for the moment, so this is kind of like the solution to part 1 I'm giving you. Assume that 1 over bn converges to 1 over b. How does that allow you to break down or prove what the limit as n goes to infinity of an over bn is? You want to get from here to there, what step do you have to go through? Break them up. How? Break them up how? Yeah, the limit of an. Limit of 1 over bn. And why is that true? How come you can say that? I'm challenging you now. How come you can say that? How do you know that's true? It's not the linear part, no. The product part. It's the thing we were engaged in a few minutes ago, proving that the proof, because an multiplied by that is this fraction. We just went to all the trouble of proving the product rule. So the product rule tells us that the limit of this thing is the product of these two limits. And then assuming you can do this, assuming that this is true then, well, we know the lit of this is a, we know the limit of this is 1 over b, so that would be equal to a times 1 over b. But that assumes that this is true. This is the special case. So once we prove the special case, this is how we'll prove the general case. That's why you prove special cases, because you kind of boil down the essential behavior into the special case, and then show how just an easy extension, or using other tools, you can then generalize it to the general case. In the product form, our special case was things converging to 0. We first considered those. Here, the special case is not the general quotient, but just a simple reciprocal, 1 over another sequence. So that's kind of the solution to part 1 there. But then 2, 3, and 4 are kind of leading you through the discovery of and the construction of the proof of this thing in the box, proof of that special case. Once you've succeeded in doing that, then it's no longer an assumption, it's just a fact, thing you know, and so this then is the proof of the general case. Yeah? So I'll pass those out to you as you're leaving, as we're going. We should turn to, so that's the, so now that's kind of tough, and I know you've got tutorials now immediately this afternoon, later, don't you? It's probably not something you're going to sit down and solve straight away in the tutorial. Maybe you will. It's maybe something to take the week over, spend the week doing it. Or, sit down for a couple hours with it tonight and figure it all out. But do it. Because you need, discovering these things yourself is definitely a good way to learn. Arguably, it's much better than watching me show you. Okay, we're not finished yet. We want to go on now to example 1.8. Okay, check it all out. Chat, check it all out. Stop. Okay, example 1.8. So here we have to figure out what the limit, and this is why why we go to the trouble of establishing those properties of convergence. What is the limit of that? Okay, that's our task. Now, what we're not going to do here is jump into a complicated epsilon argument. Okay, that's why we went to the trouble of proving those things, was that we don't have to. Let's do it once and for all. Prove the general facts, which we can then apply to these particular examples. First of all, though, consider 1 over n. What does that convert to? 0, doesn't it? We proved that a couple of lectures ago. Last week, I think. The 1 over n converges to 0. We know that. We proved it using the formal definition. What does 1 over n squared converge to? 0. Well, how do you know? It's going to go bigger and bigger, yeah. But should we go and do an epsilon argument about it? Or is there any of those properties we could use
over n, 1 squared over n.
Exactly. Good. Then he's dropping at me. 1 over n squared is equal to the product of those two. And we know that they converge to 0. So 1 over n squared should converge to 0 times 0, which of course is equal to 0. So 1 over n squared does converge to 0. Similarly, 1 over n to the power a converges to 0 for any. Let's be a bit bold. It's jumping a bit, but 1 over n squared will converge to 0 for any positive a. In one sense, you think, well, the bottom is just going to get bigger and bigger. That's true. And you can kind of see it as using product rule to put together this fact of 1 over n. So we know how all these polynomial terms will behave. So now let's look at this thing we're trying to approach here, limits of this. 2/3, 2n squared minus n, minus 3n squared plus 2. Well, the first thing we could do is take the 2/3 out. This is 2/3 times the limit of 2n squared minus n over minus 3n squared plus 2. First, you got n goes to infinity under all these limit signs. So that's using linearity. So I've got that fixed constant multiplier. I'm taking that out. Now, what's your first instinct here? The limit of something of one sequence divided by another. Which one of our properties should we use there? Quotient. So we're looking at the limit of the quotient. Okay. That's a good answer, but it's the wrong answer. Well, just not yet. We can't really apply it yet. The quotient form, thinking along the right lines, but we're not ready to apply the quotient form. The quotient form applies when you're taking a quotient of things which are convergent. But is n squared, 2n squared minus n, is that convergent on its own? No, that's unbounded. That's going to get bigger and bigger and bigger without any bound. Similarly, the minus 3n squared plus 2, that's not convergent either. That's going to get larger and larger in negative value. It's unbounded. So you can't go ahead and say the limit of this quotient is equal to the quotient of the limits, because the limit of the top part does not exist. The limit of the bottom part does not exist. We want to do mathematics, we want to argue carefully and sensibly. We certainly don't want to write down a quotient of things that don't exist. The individual things don't exist, because that would just be nonsense. Talking about something that doesn't exist. But there's a neat little maneuver which changes the fraction, well, changes the numerators and denominators, but doesn't change the overall fraction. And you understand, of course, that fractions can represent quantities, but different fractions can all represent the same quantity. And you can change the fraction by multiplying above and below by the same quantity, or dividing the numerator and denominator by the same quantity. So the thing we should use here is the highest exponent of n we have. So we have n squared still. I'm going to divide above and below by n squared. I think there's a misprint in the oh, no. I think it looks okay. Looks okay. I must be thinking of another bit. Now, why did I go to the trouble of rewriting my fraction like that? It's the same quantity, but it's just expressed as a different fraction. Now, are we ready to use the quotient form of the algorithms? Well, yes. Good. Because is this thing convergent? What does it converge to? 2. It's 2 minus something, which is convergent to 0. So we can use the linearity result to simplify that. And is 3 plus 2 over n squared converging? Yeah, to minus 3. So 2 over n squared part is convergent to 0. So now I can use the quotient. Because the limits at the top and bottom do exist. So right there, before your eyes, we've used the quotient. I'm saying the limit of this is equal to this limit divided by this limit. We have to use, again, linearity to actually evaluate these. This is going to be the limit of 2 minus the limit of 1 over n. The 2 is a constant, just has the value of 2. Minus 1 over n is convergent to 2. Similarly down here, we just end up with minus 3. So that's using linearity. And the fact that 1 over n and 2 over n squared are both going to 0. This step there was using the quotient form. Quotient form of theorem 1.4. Okay, which, strictly speaking, we should say is still on hold because we haven't proved it yet. It's your task across the week to settle on the proof of it. It is true, because I've written it in the book, of course, but you will come to appreciate why it's true when you prove it. And this is now just something to be evaluated, 4 over minus 4. So this shows how we can evaluate the limit of a complex sequence, compound sequence. What were the ingredients in this calculation? Well, the ingredients were really just the known, or the behavior of 1 over n, which we proved directly using definition 1.6. And then, see, linearity, quotient form, linearity, using these properties of convergence that we proved in general for any sequences. Here I'm applying them to instances of certain sequences. So if you look at the exercises there, exercises 1.1, there's lots of things to consider there. Lots of examples of applying these properties of convergence to be found. You have also still got, it might be outstanding for some of you, the further problems sheet. So it's that sheet I gave out a few weeks ago, further sequence problems. That will still be in play for you. And then you've also got this sheet, which is the guided construction of the proof of the quotient form. What I'm going to do, I'm going to leave a few piles of this down here. So you don't just pick one up quickly on your way out. Pick 3 piles so you're not crowding around each other. You just collect one of these sheets on your way out. And if somebody could bring the signature sheet down as they come.